Cool. It's my pleasure to introduce Ronni, who's going to talk to us about pre-events.
Thank you. Yeah, so thanks for having me. Thanks for joining us in this little pre-events session. Pre-events actually was an NSF program, and it stands for Prediction and Resilience Against Extreme Events. I think I got all of that straight. There were a few projects that were funded. We got funded to do that for volcanoes. And we, as a group of PI students and postdocs, I'll get into that, and a long list of collaborators. We split this up into two talks. Taryn's going to be talking next. I'll focus on the project overview, some discipline-specific results, data products, and some of the lessons we learned along the way. Because the initial motivation of this workshop too was to do kind of come together and do volcano-specific syntheses of data and what we know, create conceptual models of the plumbing system, and we've worked on that for 8 volcanoes at least. We've made a lot of headway. So let's get started. This is an NSF-sponsored project. Again, we analyze and synthesize existing data from past eruptions at 8 volcanoes to advance eruption forecasting. So we have these 8 volcanoes. You've heard some of those names already. Redoubt, Augustine, Boguslav, and Okmok, which are predominantly closed systems, intermittently erupting. So that's one group of volcanoes. And then another group, Veniaminov, Pavlov, Shishaldin, and Cleveland, which are more frequently erupting, perhaps open system volcanoes that we wanted to look at. The broad strategy here was to identify patterns in the data pre, co, and post-eruptively, or during those times, then develop volcanic models, both conceptual plumbing models, what's the subsurface architecture, and for some volcanoes, try to develop physics-based models, and then conduct probabilistic eruption forecasts for these volcanoes or others. Some of that actually has made its way into, say, our dealings of the unrest with Mount Spur at AVO. Okay. As I said, it's a large group here. I'm not going to be reading all of those names, but I want to point out the students and postdocs. So there were 4 students on this. Mario Angarita just defended his PhD in geodesy. Jamshid, we've already seen here. He's around. Oh, he's getting pizza. No. Anyway, he got his petrology PhD and is now working for ADGGS. Pablo is working with USGS landslides now. Got his master's in remote sensing. And Darren is also here, is going to defend his PhD on June 10th. So a lot of progress made. Well, he hasn't passed yet, but his work is very promising. I don't want to jinx it. I also want to point out Taryn Lopez, the PI. She's going to talk after me. She's done a tremendous job in kind of shepherding this unwieldy group of people through this project, keeping us on task and delivering results. So thanks, Taryn, for all of your work on this. Okay, there is a lot of collaborators. Maybe if your name is on this slide, or if you have collaborated with us, just raise your hands. Some of your people who are in the room. Come on, well, there's a long list of people. Some are also online, spread out over a bunch of organizations, more people at UAFGI, some at AGGGS, more AVO folks on the USGS side, Calvio, CVO, VDAP, University of Naples, Columbia, and South Florida. We've had a few collaborators meetings that were either virtual or in person. And during some of those, we've done expert elicitation and kind of trained ourselves to become familiar with the concept of probabilistic forecasts of eruptions, which was really quite instructive. So, okay, 2 talks that we're having here. kind of spanning the 4 project phases. The first part, that's mainly what I'll talk about, is tool development, data reanalysis, database expansion. For each of the disciplines that we had, the goal was to automate or somehow streamline 1 to 2 monitoring techniques, and then run these tools on the existing data for target eruptions. So one of the goals of or demands of PREEVENTS was to not go out and collect new data. It was really like go back to what we have and figure out what we can do with all of this to understand these systems better. We then populate or are in the process of populating an expanded AVO database. That's a part what Taryn is going to be talking about. And then volcano-specific data synthesis, model development across volcanoes, and a huge outreach and education component that we're really excited about. There was a lot of effort put into curriculum development and an outreach video and so forth. Taryn's going to talk about that too. Right now, we are completing year 4, so it was a 4-year project. COVID and other things happened. We got an extension, and we're in the process of wrapping things up. Okay, so let's walk through the individual disciplines. Darren is up here. The first project was earthquake catalog enhancement. So apply, refine, test automated methods to relocate earthquakes and detect them and get better catalogs. That involved a number of tools that are listed there. Down here, we have an example for OCMOC. This is 2008 April through September 2009, plotting frequency index of these earthquakes. The important takeaway message here is that the red earthquakes are the original AVO catalog, and the gray earthquakes are those that were detected after the fact. Not necessarily with magnitude, but you can see that there's a lot more seismicity early on in the part of unrest that was previously perhaps missed, and it wasn't as quiet leading up to 2009 as we perhaps thought. That has been applied to other volcanoes, Redoubt, Augustine, Ogmore, Boguslav, and most recently Spur. That's published in Tan et al. In 23. Here's the Spur example result, which is also really quite impressive. The original catalog of locations over here. You can see 2 clusters of earthquakes at Spur and Crater Peak, right? They're kind of switching back and forth, perhaps. What is impressive with the relocations, we actually see structures emerge that are still debate of, or the focus of debate to figure out what they actually mean in the volcanic context. But even with the network that we have at Spur, we could sharpen our view of what is going on at the volcano substantially with this, with the work that Darren did. Okay, so there's these kind of catalog enhancements have been done for a number of volcanoes here. There's match filter and relocated catalogs for Redoubt and Augustine for interesting time periods. Same for Boguslav, Trident, and Spur. There's relocated catalogs available. Some of the lessons learned here, one of the key things is that you can join these tools in single workflows, but you might not get the best results simultaneously. So there are trade-offs. You can obviously increase your number of detections by lowering the quality that you demand of these detections. That then has a result in how sharp your structures are actually going to be emerging. So that's important. And lastly here, there have been a number of impressive papers for California, Kilauea, where thousands of earthquakes are very tightly defining structures. That's not necessarily possible in Alaska, given the networks, given the data outages that we're dealing with. So there is some care that's necessary to optimize the tools, but there's a lot of knowledge that can be gained. Darren's second project was tremor detection and characterization using machine learning. That is published in TAN and others in 2024. And he developed the Volcano Infrasound and Seismic Spectrogram Network, or VoiceNet, which is 2 convolutional neural networks one for seismic and acoustic, to detect and classify tremor based on spectral signature in near real time. There's an example down here. Originally, this was all trained on Pavlov 2122 data and then applied to the other eruptions. Here, there's one station example, station PN7A. And up here, we have that colored bar of classification that VoiceNet came up with in different tremor classes, earthquakes, long period explosions, and noise. Down here, we have the spectrogram for comparison. And you can see there's a lot of broadband tremor that kind of trades off with other tremors before then on February 24th. So this is just one day of data, or just a few hours of data, actually. We see more earthquakes emerge. So that actually allows us to, at very high rates, classify the progression of these eruptions. For the entire network, there is also station-based voting and so forth that is happening. All the details are on that paper here. Cool. David Fee and others generalized VoiceNet using labels from 6 other volcanoes to apply this more broadly, not just to Pavlov. These models are open source. David's paper, I think, is currently in press at Volcanica. They're open source and could be run on Alaskan volcanoes if the data are on IRIS. For Pavlov and Shishaldin, we have generalized VoiceNet classifications for the seismic data over 20 years. Lessons learned, sanity check, anything that you're doing with machine learning. There's all sorts of cool stuff that could happen that doesn't have anything to do with what the volcano is actually doing. The seismic models are promising for Pavlov and Shishaldin, but should best be used in similar settings. And the infrasound model doesn't perform quite as well, and isn't as transferable, which is due to a lot of the caveats of the training data. Cool. Mario worked on geodesy problems. His first project was Mozart, morphology from SAR toolbox. The idea here was that we have SAR amplitude data, and we rarely do anything quantitative with them. There's useful knowledge in there. Usually for INSAR, we use the phase data only and throw the amplitudes away. So Mario went the other path and used the intensities to get at elevation changes. So this is just animations time series here. For the blue dot, you can see there isn't really anything going on. The range here is ±5 meters. So this works for a lot of deformation, not necessarily small INSAR type things. But in the crater area, we actually see tens of meters of change as the eruption is happening, and there's higher fidelity work done. And this has been applied to Shishaldin, Cleveland, Okmok, Boguslav, Great Sitkin, helping us to quantify these surface changes. That's available on GitHub. It's fully written in Python, has been applied to a range of SAR platforms, could be used on other SAR platforms, and there isn't really a restriction to be using that in Alaska. Importantly, though, it should be used only for small regions of interest, because it is based on the reflected amplitude, and so surface properties affect that. So if you have a lot of change in water content, for instance, that might affect this. So there's care that's necessary here. Second project is VMOD, modeling of deformation inversion framework. Easily expandable, written in Python to integrate a range of geodetic observations. Use SAR, INSAR, ascending, descending, GNSS observations. Be able to run joint inversions and multi-source geometries. Has been applied to a range of volcanoes, and here's an example for Westall and Fisher, where we use both ascending and descending INSAR to invert for a dual source model. Similarly, we use continuous and campaign GPS. So this is all informed by one inversion, which is really neat to be able to do that. Lessons learned, or this is open source and available. Python has been applied to a range of data. We use it routinely for SPUR and other unrest. It is a Bayesian framework, so posterior distributions are critical to actually get a better understanding of the parameter space. So how reliable are the values that you're calling your best fit actually? And because of that, there's some fine-tuning that is useful because of the computational needs in these types of inversions. Right. Pablo worked on automatic identification and quantification of volcanic hotspots. He developed and tested HotLink, which is a machine learning approach to detect thermal signals and calculate radiative power that has been applied to VIIRS and MODIS data for all the PREEVENTS volcanoes. And here's an example for Veniaminov, where the HotLink radiative power is compared to Mirova radiative power, and you can see they agree very well when the volcano is actually starting to do something. There's a separation in day and night because that is actually important. One of the lessons learned here is that water and land heat up and cool down at different rates. That can cause false positive hotspot detection. So using nighttime imagery is actually advised here. Okay. The data are available for these target volcanoes published as a Python package. The second project is more manual, where the remote sensing group is using tropomi data to get at SO2 detections, calculate masses, and record that in the database. There is detectable degassing that varies substantially with the activity and spans about 4 orders of magnitude in SO2 emission rates. They've done that now for 5+ years, and 12 volcanoes have 600 more detections. You can see some overview here also of the range. A key point to take away is that satellite SO2 emission rates are typically underestimated when compared to airborne. And observations are sparse in the winter due to lacking UV. Jamshid already talked about this, diffusion chronometry. So I'll be brief on this. The idea is zoning history of minerals can record the magma system perturbation, and modeling this can help resolving the timing of events. So he talked about Bogoslav eruption, where we have mafic recharge in the months before the eruption, and then syneruptive decompressive magma ascent that is being recorded. For readout, we also find in the decades actually before the 2009 eruption, interesting signals that suggest mafic recharge. This is published in JVGR paper that includes the timescales and is compared to monitoring data. Diffusion chronometry is powerful to calculate the process timescales, but it doesn't really tell you much about the actual process and requires prior knowledge. Project 2 helps with the process identification using multi-phase crystal clusters here to determine how these magma processes can be responsible for these kind of zonation patterns, right? So we can have these different zonation patterns at individual crystals for a large host of reasons, but together the idea is that tells us in some decision matrix what the actual process was. This is currently in review, has been applied to readout in Bogoslav, and OCMOC is in progress. So Benaz and Carly Ross are working on that at MSU. Lessons learned, it's difficult if you don't have many crystals, and the more phases you have, the more precisely you can get at the process. Okay, last slide. The summary here is that these new methods can bring substantial improvements to already existing data and find new signals, and there's a lot of data left, right? We have many volcanoes. We only looked at 8 and not necessarily completely. There's still human intervention that's necessary for fine-tuning, QC, and interpretation, even though machine learning makes things a lot better. There's a lot of special challenges. Some of those have already been mentioned, but there is network densities and environmental conditions or outages that need to be considered, especially when you're transferring methods. But once all of these methods were there, the engagement in collaborations within PREEVENTS and beyond was really quite impressive. So having new methods and applying them to data is really exciting. Cool, thanks.